Okay, next we have the common emitter output characteristics. So here we have the transistor. Okay, this is the collector, and this is the base, and this is emitter. So this is collector, this is the base, and this is emitter. And now this is the common emitter case. So the emitter is keeping common between base and collector, and now this is junction J1 and this is junction J2. Now the transistor is acting in negative mode, so it means that this junction J1 is forward bias. So this is NPN transistor. If it is forward bias, then this P side of this junction is connected to positive terminal and N side is connected to negative terminal. So this is the battery VBB, and here the voltage appear across this base and emitter. This is emitter. Okay, so the voltage appear across base and emitter is VBE, because base is connected to positive terminal, so base is come first, and emitter is connected to the negative terminal, so emitter comes next after base. Now junction J2 is reverse bias, so it means that this N side is connected to the positive terminal. Okay, and the other side will automatically be negative. So this battery I call it VCC, and the voltage appear, the difference in voltage appear between collector and emitter is represented by VCE. Why VCE? Because C is connected to the positive terminal collector and emitter is connected to the negative terminal. Now the voltage appeared between base and collector will be VCB. So the voltage appeared between base and collector here will be VCB. Now this is the emitter current. The emitter direction of emitter current is outward, while the direction of collector current and base current is inward. So here the input current is the base current, the input voltage is the voltage between base and emitter, the output current is collector current, and the output voltage is the voltage between collector and emitter. Now common emitter output characteristic can be defined as, it is the graphical relation between output current IC and output voltage VCE by keeping input current IB constant. Now so it means that I will plot the graph here. So it means that the output characteristic will be the graphical relation between output current, output voltage VCE and output current IC. Now we know that IC is a big current, so we measure it in the unit of milliampere, and this output voltage is in the unit of volt. Now we already derive a relation for the common emitter characteristic that the output current IC is equal to beta IB, which is the input current, plus beta plus 1 ICBO. This is a well-known relation we derive for the common emitter characteristics. We can also write it is IC is equal to beta IB plus ICEO. Now here we use this supposition that ICEO is equal to beta plus 1 ICBO, and this ICEO this ICBO is the leakage current or the reverse saturation current in case of common base, and ICEO is the leakage current or the reverse saturation current in case of common emitter, while taking the third terminal open, like if we have emitter and like by collector and emitter junction, sorry, this is the reverse saturation current in common base characteristic, where the collector base junction is operating while the other third terminal, like the emitter terminal, is open. Here the collector emitter junction is the collector and emitter, they are operating while the third terminal, which is base, is open. So these are the reverse saturation current. Okay, this is the reverse saturation current. We also call it leakage current. Now we have to plot a relation between the output voltage and output current by keeping the input current constant. Okay, now if we look at here in this equation, then we see that if we look at this equation, IC is equal to beta IB plus ICEO. Now if the input current I take the input current IB is equal to 0, like we start from 0 and then we increase the input current, let's say from 0 to 15 volt, and then 15 micrometers and so on, then what will be the situation? If IB is equal to 0, then from this equation IC is equal to IC. So the output current is only due to the leakage current or the reverse saturation current, and we know that the reverse saturation current is of a diode is like this. Now this is the reverse saturation current ICEO, which is equal to beta plus 1 ICBO. Now the region under this curve here, this curve is called cutoff region. This is the cutoff region. Now here ICEO is the leakage current or reverse saturation current, and we know that ICEO is always greater than ICBO. Why? Because you know that ICEO is equal to beta plus 1 ICBO. So there is an extra term beta plus 1 which is multiplied with this ICBO. So that's why we can say that ICEO is greater than ICBO. Now as we increase the input current, let's say if I increase the input current from 0 to, let's say, 10 micro ampere, and then from 10 to 20 microampere, and then from 20 to 30 microampere, and so on, then what will be the situation? The graph will look like this. Here again I will use the same graph, but I will plot in a different page. So here this is the okay, this is the output current, which is measured in milliampere, and this is the output voltage VCE, which is measured in volt, in the unit of volt. Now here I have a situation like this. This is the saturation current, or the reverse saturation or leakage current, and this region is called active region. And this is the case when the output current IB is equal to 0. Now as we increase the output current from 0 to, let's say, if IB is increased from 0 to 10 microampere, then what will happen? The output current or the input output current will varies with output voltage like this. This is for IB is equal to 10 microampere. If I increase the IB value from 10 microampere to, let's say, 20 microampere, then the situation is like this. If I further increase IB from 20 microampere to, let's say, 30 microampere, then it will behave like this. So the current, the output current, varies with output voltage like this. Now here the region under this curve, this region, okay, this is called active region. Active region. Now if I see the equation, IC is equal to beta IB plus ICEO. Then from this equation we see that IC is independent of VCE, because there is no dependency of IC with VCE. But if I look at here, if I see here, we can see that as we increase VCE, then IC also increase a little bit, because the graph looks like this: VCE, and this is IC. It varies like this. So there is a variation, there is a change in IC with change in VCE. Why? Because of the early effect. Because in early effect, VCE is the reverse voltage, so it's increase the effective width of, this is the, let's say, the width of the base VB. If we increase VCE, okay, so the width of the junction increases, so this is the W, and the effective or the net width is this one. Now if VCE is increasing, what will happen? Then the effective weight, okay, this effective weight is going to be decreasing, is decreasing. If W effective is decreasing, it means that there is a less recombination of electrons and holes in the base region. If there is a less recombination of electrons and holes in the base region, then what it means? It means that most of the electrons which are coming from emitter to the base goes to the collector, so the collector current increases. So this implies that IC is increasing. So that's why we see that there is a small variation, but the variation is not too bad, but there is a increase in the collector current as we increase the VCE, even though from this equation we see that IC is independent of VCE, and this is because of the Orley effect. Now the region left here, this region, which is, let's say, the point O, and this is the point A, then this region is called saturation region. And this is the region between the knee voltage and the knee line OA. Now here in this region, both the junction J1 and J2, they are forward bias. Now next we have to derive a relation for the dynamic output resistance. The dynamic output resistance of common emitter characteristic is equal to change in output voltage delta VCE over change in output current, which is delta IC, by keeping the input current IB is equal to constant. Now the relation is now given by delta VCE over delta IC, and this value is very small because the reason is very simple, because the change in delta IC or the change in IC, which is delta IC, is small for a large change in VCE. Because if we look at here, if I take a large value of VCE, let's say from here to here, this is, or I can use a different color pen. Like if I take a large VCE value, let's start from here to this point, this is delta VCE. Then the change in IC, this is delta IC, is very, very small. So change in IC is very, very small for large change in VCE. Like if we change VCE, for a large change of VCE, there is a small change in IC. So if there is a small change in IC, then it means that this quantity will be small. So this is all about common emitter output characteristics. In the next video, I will discuss common collector configuration of a transistor. Thank you.